Time and place, or you tell me what time it is, and I'll tell you where you are. There is a very advanced technology that we've come to rely on every day to find out where we are and to get us where we want to go. We use it in our smartphones, we use it in our cars and boats, and we use it when traveling in the backcountry. That technology is GPS, the Global Positioning System, officially known as the Navstar Global Positioning System. The system was originally developed by the U.S. military for their own use, but has also been made available for general civilian use. Today, we're going to learn a little about how GPS works to give us precise location information. In order to better understand some of the basic concepts behind GPS, let's first talk about some older, more traditional ways of determining our location. The first is relationship to known objects. Sometimes we determine our location just by looking at the position of familiar objects around us. There's the City National Bank on that corner, the First Methodist Church on that corner, and the U.S. Post Office on that corner. So I must be at the intersection of 5th and Ferry Streets. We can do a similar thing, but in a more precise way by using a map and a compass. It's difficult to imagine doing this here where the land is relatively flat and forested, but suppose I'm in the Idaho desert. There I can see for miles and miles, and I can use a method called triangulation. There's Taylor Mountain, and my compass tells me it's at a bearing of 095 degrees. And there's Saddle Mountain, it has a bearing of 355 degrees. I can also see Table View with a bearing of 040 degrees. Now if I plot those three lines of bearing on my paper map, they all cross in one place, and that's where I am. Note that on its own, each line represents all possible locations that have the given bearing to that specific landmark. But there's only one place on my map that can have those three specific bearings to those three specific landmarks. Note that I could have stopped with two bearings, but by using three, I eliminate the possibility that one or both is in error. If one or more of my bearings is wrong, then all three lines won't cross in the same place. Note that so far, we haven't had to concern ourselves with time. That's because everything in this example, me, my map and compass, all the landmarks, are stationary and not moving relative to one another. What do we want to take away from this example? Three things. The location of the mountains is shown on my map. I know where I am relative to the mountains, and that will let me find my location on the map. Now let's talk about celestial navigation. For hundreds of years, people have used observations of the sun, planets, and stars to help determine their location. Because we're in motion relative to the sun, planets, and stars, and their observed positions are always changing, knowing the precise time will now become critical. To make the necessary observations, we would use a sextant. With a sextant, we can make precise measurements of the elevation of the sun, planets, and stars. Again, because of the relative motion, we have to include the precise time with our measurements. After we measure the elevation of a star, we would refer to a special data table known as an almanac. The almanac would tell us the exact spot on Earth where a specific star would be at the zenith, that is, directly overhead, or 90 degrees, at the exact time of our observation. Then, using our measurements and a bit of spherical geometry, we can calculate what is known as a line of position. That's a line on our map representing all possible locations where the star would appear at that elevation. Observations of a second star would let us draw a second line of position. Where those lines cross would be our location. Shooting a third star and calculating a third line of position would allow us to verify that it crosses in the same place and helps to confirm that we haven't made a mistake. Oh, and by the way, if we were to view those lines of position from outer space, each one would be a complete circle on the Earth, a concept that we will see again in just a few minutes. What is our takeaway from this example? 4 things. We can measure the position of a star relative to us at a specific time. We can look up information about the star in a published almanac. From that, we can calculate a line of position, and multiple lines of position will help us find our location on a map. Let's begin to put all this together. We're going to continue with the concepts of using relative positions and observations of known stars to determine our location. Except, let's make our own stars, artificial Earth satellites, and let's design those stars so that we know exactly where they are at all times. And so we don't have to wait for a clear night sky to determine our location. Let's have those stars share that information with us via our radio signal. And finally, let's design those stars so that they know exactly what time it is and can share that information with us also. Knowing the position of our stars, the GPS satellites, in the sky, and the precise time will let us determine where we are using a technique called trilateration, which is similar to triangulation, but uses distances instead of angles. So now on to GPS navigation. To find our location using GPS, we need a GPS receiver. That may be a dedicated handheld device, your smartphone and an appropriate app, or a device built into your vehicle's dashboard. It's important to remember that the receiver doesn't talk with the satellites, it only listens. The receiver contains an accurate quartz clock, and it uses information coming from the GPS satellites to set that clock and keep it set. The satellites themselves contain extremely accurate atomic clocks, accurate to within 3 nanoseconds. By comparing the exact time transmitted by a satellite with the exact time indicated by its own clock, and knowing the speed of the radio signal, which is the speed of light, the receiver can calculate how far it is from the satellite. We'll discuss exactly how that works in a few minutes, but first we need to understand some additional concepts. Knowing our distance from a satellite tells us our position relative to that satellite, but really it only tells us that we're located somewhere in space on the surface of a sphere, a precise distance from that one satellite. What if we use our receiver to measure the distance to another satellite? That would give us another sphere of possible locations in space, and where two spheres intersect, that makes a circle. So now we've narrowed our location down to somewhere on a particular circle in space. If we add a third satellite, we'll find that each sphere makes a circle on the other two, and all those circles will only intersect in one place, and that's where we are. The intersection of three spheres in 3 dimensions is extremely difficult to visualize, but it might help to remember that they also have to intersect with a fourth sphere, the Earth. If we hide the satellites in this graphic and only show where the spheres of location intersect the Earth, it will look something like this. Notice that this looks a lot like those lines of position from traditional celestial navigation. So now we know exactly where we are relative to 3 different satellites somewhere in space. But for that to be of any use to us, we need to know exactly where those satellites are. So how do we know where the satellites are? Well, objects in space can be tracked with great precision. The U.S. Air Force knows exactly where each of the 27 Navstar GPS satellites is at all time, and uploads that information to each of the satellites. In turn, the satellites transmit that information to our GPS receivers as a set of data known as an almanac. The almanac is stored locally in your receiver and updated frequently. You can also receive updated almanac data over the internet, and many GPS receivers make use of this, especially our smartphone apps. If you're using a dedicated GPS receiver or smartphone app, you may see a display that looks like this as soon as you turn it on. The receiver already knows about where the satellite should be from its almanac data, which helps it to start acquiring their signals and to begin making location calculations. Now we have everything we need to find our location. Our receiver knows where the satellites are relative to the Earth based on the almanac data, and it has calculated our location relative to those satellites. Our receiver also contains a map of sorts, a mathematical model of the Earth's surface known as mean sea level. All that's left to do is to communicate the location information in a manner that we can use. That might be by giving us numerical map coordinates or by showing us our location on a map display. One other thing, that location information includes not only horizontal position, but also altitude relative to mean sea level. There's just one thing we need to know to make our understanding complete. We need the exact time in order to calculate our distance from the satellites and to look up the satellite locations in the almanac. How do we know what time it is? The clocks on board each satellite are very precise atomic clocks, and they are all synchronized with each other and with master clocks on the Earth. That's not as easy as it sounds because of relativistic effects. Clocks on the Earth run slower than clocks in space because they are closer to a source of gravity. But clocks on the satellites run slower than the clocks on Earth because they are moving relative to the Earth. As tiny as these effects are, if the GPS system didn't make automatic corrections for them, the accuracy of the system would degrade to unacceptable levels within a matter of minutes. The clock in your receiver or your phone or your car or whatever is accurate, but it's not an atomic clock. So it must constantly be corrected and synchronized with the satellites. That's not an easy thing to do. We can't just set our receiver's clock to match the satellite's clock because it takes a finite amount of time for the satellite signal to travel to us. That time varies as the distance to the satellite varies, and there are multiple satellites sending us time signals, each at a different distance, resulting in a different time delay. How clock synchronization is accomplished is beyond the scope of this presentation. For now, just understand that it's accomplished using some very clever tricks of mathematics and geometry, and by using the signal from a fourth satellite. Now that we know that the satellite and receiver clocks are synchronized, we can better understand how to use time to calculate the distance to each satellite. Suppose, and this is a very simplified example, your GPS receiver receives a signal from a satellite that says, "It's 1 p.m." The receiver looks at its own internal clock and says, "Well, down here it's 1 p.m. plus 65 thousandths of a second." The receiver knows it took 65 thousandths of a second for the signal to arrive, so it can calculate that the satellite is 12,000 miles away. Starting with basic location information, we can build all sorts of sophisticated features into a GPS receiver or app. Once your position is determined, it can be redetermined continuously. From there, it's simple for your receiver to calculate your speed and direction of movement. If the location of objects of interest have been stored in the receiver's mathematical model of the Earth, then your receiver can tell you the direction and distance to those objects. And if that mathematical model includes such things as roads and streets, then your receiver can be designed to calculate routes from one place to another and tell you when you should arrive. Note that all that information about maps and things around you is stored locally, and all the calculations related to speed, distance, and routing are also done locally and are not a part of the Navstar GPS system itself. Another benefit of GPS is that your GPS receiver, or the GPS application on your phone, gives you access to an atomic clock accurate to within a millionth of a second, and you have free access to it from a tiny device that you can hold in your hand. Remember this the next time you need to set your watch. So that's basically how the Navstar Global Positioning System works to give you amazingly accurate information. Civilian use has come a long way. Way back in the 90s, the best we could do was read some numbers off a tiny LCD screen and plot them on a paper map to determine our location. From there, we could do our own measurements and calculations to determine the distance and route to our objective. Now we have color moving map displays that show us exactly where we are within a few feet, tell us how fast and in which direction we're moving, and how to get where we want to go. The Navstar GPS, with Navstar GPS, you have access to a multi-billion-dollar system from a tiny device you can hold in your hand. The uses are limited only by your imagination. Just as with the internet, it's difficult to imagine a time before it was available. So, do we have any questions?